Hello everyone, my name is Shunli Wang. I'm a PhD candidate at the Academy for Engineering and Technology of Fudan University. It's a great honor to introduce our new work here. The paper I will present today is titled CA-SpaceNet, Counterfactual Analysis for 6D Pose Estimation in Space. My speech consists of 4 parts. Firstly, we will briefly review the background of the pose estimation task and our motivations. Secondly, we will introduce the proposed CA-SpaceNet in detail. After that, the experimental results will be shown. And finally, we will summarize this paper. Reliable and stable 6D pose estimation in space plays an important role in space missions. For example, the NASA's SpaceX docking mission and the Clear Space project. Compared with terrestrial applications, many factors should be considered, such as harsh imaging conditions, background interference, and limited computing resources. To address the first challenge, complex background interference, we consider that how can we remove harmful elements from the composite features. Then we propose the CA-SpaceNet to handle harmful background in aerial images. To address the second challenge, limited computing resources and power consumption, we consider that how can we achieve efficient deployment of models in low-power scenarios. We carry out low-bit quantization strategy and deploy part of the network to a processing memory accelerator on FPGA. Secondly, we will introduce the proposed CA-SpaceNet in detail. The question becomes, how do we translate the counterfactual thinking into the actual network structure? Our solution is to construct 3 different paths. The factual path that extracts the feature of the whole image, which is colored in green. The counterfactual path that extracted the feature of the background information, which is colored in red, and the procedural counterfactual path that mimic the output feature of the counterfactual path, which is colored in blue. Simplified chiral graphs of the CA-SpaceNet in 4 situations are shown in this figure. These figures clearly illustrate the principles behind the chiral reasoning. After obtaining these features by 3 paths, the total direct effect can be calculated by subtracting the side effect from the total effect. The CA-SpaceNet can remove the harmful background interference from factual features and generate accurate pose results, which cannot be easily identified by traditional models. The training and inference phases are separate in CA-SpaceNet. All 3 paths are activated during training, while the real counterfactual path is removed during inference due to the absence of the ground truth mask information. We adopted the classical LSQNet to quantize CA-SpaceNet to a low-bit width model and then deploys a 3-bit convolutional layer into a PIM accelerator on FPGA. In order to explore the influence of quantizing different parts on the performance of CA-SpaceNet, 3 quantization modes are set up. The details of quantize of convolution are shown in these steps. Note that the batchnom layer is merged into the single-step operation. Next, the experimental results are discussed. Comprehensive experiments are conducted on SwissCube and SPEED datasets. Quantitative results on the SwissCube dataset show that the CA-SpaceNet can eliminate the interference of background under the medium and far settings. Results in Table 2 show that the performance improvement is brought by the counterfactual analysis strategy rather than the additional 30 training epochs. Qualitative results show that the CA-SpaceNet can significantly reduce background interference and generate robust pose estimation results. Then we quantize the framework into 3 and 8-bit and deploy part of the quantized network to a PIM accelerator on FPGA. We evaluate the performance of the deployment from the aspects of GFLOPS saving ratio, model size, and latency. Experimental results confirm the superiority of our strategy. Our real deployment of the PIM accelerator on the FPGA achieves almost 4 times faster than the ARM CPU and 2 times faster than the Intel Core i7 CPU. Finally, we will discuss the conclusion. In this paper, we propose a framework named the CA-SpaceNet, which is robust to the interference of complicated background information. Our approach outperforms state-of-the-art on the challenging Swiss-cube dataset and achieves competitive results on the speed dataset. We quantize the CA-SpaceNet into a low bit width model and deploy a part of the quantized network into a processing in-memory chip on FPGA. Low latency proves the feasibility of our method. So we believe that our exploration can bring in new contributions to the computer vision and space technology community. That's all. Thank you very much.